Thank you. Good afternoon, everybody. My name is Akhilesh Govius, and I'm one of the founders of SpectX. And today I'm excited to share how our AI-powered drone swarm system is enabling real-time sea state prediction, redefining how offshore operations are monitored and executed. To give you all some background on SpectX, what we do and how we got here, in 2021, we started building an aerial X-ray inspection system, a dual drone platform that is designed to perform non-contact X-ray inspections of large composite structures such as wind turbine blades. So in theory, we had two drones, one carrying an X-ray source and the other with a digital detector autonomously launch from a takeoff location. And they could fly with precision near the inspection target and precisely align on opposite sides. For example, in our case, a wind turbine blade. Once in position, the source drone would start emitting radiation which passes through the drone and through the wind turbine blade and then is captured by the detector drone on the far side. From this, we started generating 2D radiographs similar to what you get in a hospital scan, but generated 100 meters above the ground or water if done offshore. These radiographs were then streamed into the cloud where we did a lot of fault detection, identifying different defects like the ones I will show you in the next slide, and also doing damage severity grading, which gives kind of a repair advice for O&M operators. So we were basically digitizing inspection and delivering actionable diagnostics autonomously offshore. What you see here is some of the X-rays that we took of 33-meter V66 decommissioned blades. So after their operation and put them into our defect detection model based on deep learning, where we could detect different structural defects which could actually cause the buckling or breaking of these blades. In the course of this project, we developed quite some expertise in computer vision because it was impossible to fly these drones manually and position them accurately. And we used quite some machine learning for autonomous navigation. We also developed some expertise in developing drone hardware, and we built several platforms along with this one. The one you see is we built it along with Avular, based in Eindhoven, here in the Netherlands, which could carry payloads of up to 13 kilos. So these drones were already capable of flying quite stable offshore, and we could take all of the data that we took from these X-ray drones and put them back in an asset management portal like the ones you see here, where you could basically go on a blade view, where we ran damage severity analysis based on these X-rays we took and the 3D models. The turbine view, which aggregated blade level data to show real-time condition, and also the wind farm view, which gave operators overall turbine health, inspection history, and some idea of the structural health of the asset portfolio. So doing a lot of offshore operations, we were looking quite closely into operations such as installation of offshore wind, installation or laying of cables, or currently a lot of projects on decommissioning of oil and gas platforms in the North Sea, which are vulnerable to rapidly challenging sea conditions. So, despite decades of progress, some of these real time environmental variables were still limited to bulky buoys that these vessels would drop near the vessel or sporadic frequency domain satellite updates. So, earlier this year, we started a new project to develop a dynamic drone swarming system, sensor rich, autonomous, and backed by AI to enable continuous sensing, adaptive response, and predictive foresight right at the source of operation. Some of the offshore wind installation activities that we were looking into, specifically the installation of large steel piles or the foundations of these turbines, the monopiles, or the installation of the transition piece, which has the boat landing, the tower of the turbine itself, the nacelle, the hub, the blade, and the laying of inter-array cables and export cables, which eventually bring you the power back from these wind turbines to an offshore substation and back to land. So these operations are high stakes, precision driven, and whenever we are installing monopiles or laying inter-array cables, the weather windows, especially in the winter, are narrow. As also the industry started installing bigger and bigger wind turbines, the vessels that are in the market were currently operating at their limits, and which means that one misjudgment could lead to a costly downtime or even worse. So to tackle this problem, Spectex came up with this nowcasting solution where we wanted to predict the actual wave hitting the vessel doing heavy lift or installation activities. So nowcasting is actually where the magic of time sensing meets predictive foresight. What you're seeing here is how our system actively tracks and predicts wave states in the vessel's immediate operating environment. On the left side, we have the flight logic architecture for the swarm of drones, where each drone receives environmental inputs and path planning data and then feeds this to its onboard NVIDIA GPU with the perception module and its flight controller unit. What this does is it allows for it to react not just to planned paths, but also dynamically avoid hazards or obstacles. So we had this centralized obstacle avoidance system which could aggregate point clouds and perform these complex maneuvers across the swarm, ensuring safe flights. On the right, you see the high level architecture of this system where we wanted to fly a swarm of 10 to 25 drones around a vessel as far as we could, where these drones created a distributed sensor grid, each projecting or looking downwards to generate live wave data. As the ocean evolves, the swarm actively could follow the wave front. So basically, if there was a wave going in a particular direction, depending on whether it's a swell wave or a wind wave, we could adjust the swarm to follow this pattern based on live drone measurements, but also based on numerical ocean models. So we had this hybrid sensing approach allowing us to project wave motion and sea surface dynamics several minutes ahead with localized accuracy. All the data that we could capture was streamed to the cloud where we could process and analyze, where we run trained machine learning models to convert sensor readings into actionable sea state forecasts. So in the end, operators or the captain of the ship can anticipate conditions like swell height, direction, or rapid shifts in waves, not minutes after they happen, but a few minutes before. And that basically became the core of our new casting engine, a dynamic drone swarm integrated with real-time data fusion and predictive AI, all working together to stay ahead of the curve. Here's a system level architecture on a high level where we could have a swarm of autonomous drones around the vessel. The number of drones was actually decided by what operation you are performing offshore and the current weather condition. Each of these drones had specific sensors, which could, for example, radar, eye time of flight, and atmospheric sensors, which could collect multimodal data. And these drones could communicate over a resilient, redundant mesh network. All of the sensor fusion data was streamed back into a Azure hosted cloud, which processes this information continuously to reconfigure the swarm and generate uh, insights for these operations. Talking about what sensors we're currently using, every drone is kind of like a compact multi-sensory observatory. So we had basically a 77 gigahertz radar, which gave us long-range wave profiling. This could basically detect wave crest geometry and motion up to 100 meters distance. We also then had on top of this a stereo vision and eye time of flight cameras like the Z2 that you see here, which allows us to build a photogrammetric sea surface in near real time. So this actually could give us the spatial resolution that's fine enough to resolve patterns, especially in choppy seas. We also use atmospheric sensors like the Bosch BMP 388, which has a pressure sensor plus a temperature, humidity, and a 3D wind sensor, which for us was really important in understanding the gush shear and other parameters such as wave wind coupling. So this raw sensor data needs to be taken and then fused, and we are currently trying to do spatial temporal alignment using Kalman filtering and IMU coupled time sync. The multimodal fusion also uses the feature of confidence weighting, where radar gives us solid phase data but suffers near the vessel's wake, but vision compensates for this to give you then the higher spatial resolution. We also interpolate across sensor dropouts, take into account vibration noise from the IMU that we get, and then resolve and make predictive corrections against the short-term wave forecast. So in the end, you have an output which is a robust 3D surface map continuously updated along the swarm's collective field of view. So basically, now instead of dropping a lot of expensive buoys near the vessel, we could basically get a high resolution stitched together sea surface, which was more accurate than the buoy system. So how do 10 to 25 drones fly together reactively in a volatile offshore zone without crashing into each other or crashing into the vessel or the turbine tower or the lifting blade, for example? So each drone operates on its own local autonomy. So we have a decentralized behavior. For example, the potential field collision avoidance, adaptive altitude control, visibility aware spacing, and we also had on the vessel a ground control station, a global or a global swarm coordinator or a director based on the backend of Azure, which was continuously ingesting all this sensor data, taking into account the vessel telemetry and forecast data to basically redefine this in real time. So this hybrid architecture uh, could be also adopt these swarms. So if we were performing some heavy lifting operation, then we could tighten the drones around this crane boom and restrict for lateral flight zones. Now that we've collected and sensed this data, what do we actually do with it? So we have, like I said, live sensor data from the swarm of drones at different points. So these are returns from the radar, time of flight, and wind and pressure fields. We also have the 6 degrees of freedom data from the telemetry of the vessel, including its active operation status. But we use numerical forecast models like SWAN and SWASH. These come from Deltaris, which is a research institute. And we basically, for temporal wave prediction, we use recurrent neural networks like long short-term memories trained on both historical data that comes from these buoys or drones that collect data in real time. So these can basically learn periodicity, wave group propagation, and phase shifts. For spatial interpolation and mapping of the sea state, we uh, we are currently trying to use CNNs on elevation maps to capture cross-drone correlations, the bathymetry, so the seabed itself, and fetch directionality of the wave. What's unique in our approach is we actually don't fully replace a physics-based model because this is very computationally heavy. We accelerate and correct these models. So we use AI layers to bias correct and dynamically retune these SWAN models based on actual observed waveforms. So this year we're going to try domain adaptation for simulation to reality transfer. So we can fine tune models originally trained in the simulation, but using live operational data sets from the actual field. We are also trying to look into different uncertainty quantification techniques. Also, what happens when the bandwidth is limited. So in the end, the operator gets some kind of a risk profile. For example, that there is a 85% chance of a 2.5 meter wave within the next 8 minutes with plus or minus zero point 0.2 meters, for example. So that is actually actionable intelligence and not just raw data. With these AI models, like I said, first we use RNNs like LSTMs, which are designed to process real-time series data. We also feed this in sequence of wave measurements from our drones, and the model learns to predict what's coming next. This actually includes the height of the wave, the period of the wave, how slow it's going up and down, and also its direction, all forecasted minutes into the future. So these models are currently being trained both on the live swarm coordinated data, but also some data from the buoy and in combination with simulation data sets. We're currently also developing hybrid physics plus AI models, which helps us to combine strengths of classical ocean models like Swan or Swash with deep learning. So the idea here is quite simple. We use the physical model to get a baseline and then let AI refine on top of it, which then allows us to improve the accuracy in nearshore conditions and also reduces simulation times simultaneously. These AI layers, they act as a corrective shell, learning to adjust physics-based computationally heavy outputs in close to real time based on what the drones are actually observing. All of this then culminates into an operational dashboard, so we can see the live feed from any of these drones. So you can actually see if you actually fly 30 minutes away from the vessel, which for us at the moment is not possible given the restrictions uh, on communication and the drone battery life itself. You can see these waves develop from quite far away. We can also see AI models feed the short-term sea state into nowcasts. The system can flag risks. They can suggest repositioning of the vessel depending on which direction the wave is going, and also give some advice to the operator or the package manager on these vessels on some go no go calls. So this actually empowers the crew with predictive clarity, not just reactive awareness. At the moment, the vessels get data from the satellite, which is frequency domain. So if the data from the satellite says the wave is 2.5, there's a small probability that it could be 2 or 3 meters, depending on what the distribution is. So small glimpse into the actual mission flow. We have the drones that can launch from the deck station or the helipad of the vessel and form a dynamic grid. We also take the initial wave sea state to actually decide where to send these drones first. These drones then collect wave and atmospheric data across these layers and different directions. The system then can train on region-specific data to predict wave behavior on where the vessel is based on what the drones observe quite far away. This is a research project funded by the RVO from the Dutch Ministry of Economic Affairs. In this project, we're actually combining four other companies or research institutes, Delta N, which is an expert in machine learning and data processing, who's helping us uh, make these computations faster and in close to real time. We have Deltaris, which actually models they've modeled the North Sea, so they have really accurate wave models or ocean models. TNO, which is a research institute looking into decision-making tools, which actually then helps the offshore wind operators or contractors performing these operations, and Delft University of Technology, which is currently looking into sensor fusion and real-time data transmission. This is a low TRL project, and next year we aim to perform a live demo at the Hollandse Kust West wind farm at in the North Sea, close to the shore of Amsterdam. What's next for us? We've realized that the quads that we're building don't have long ranges, or they have limited battery life. So we are looking into hybrid drones. We will spend the next couple of years trying to gain some expertise in building these hybrid fixed wing platforms that can really cruise longer, which is basically better for the ocean. We To bring down the cost of such a system, we actually need to hopefully do this purely using optical sensors. At the moment, radars and these other time of flight sensors are expensive and heavy. And next year, after the live demo, we would like to integrate this into broader offshore operational platforms. Thank you for your attention.